Okay, welcome everybody to a demo lecture. I'll be uploading this to YouTube. This is for my 300 level Mesoscale Meteorology class. Just going to put it on YouTube so I can solicit any comments, possibly from the crowd. But before we do get started, a couple things. I assume all students in this class have a background in atmospheric dynamics, thermodynamics, and synoptic meteorology, and have also completed coursework in physics and calculus. Some of the board work we'll be doing later on will get rather mathematical and technical for some of you. So I won't be able to answer every single question you might have about some of the calculus there we're going to be doing. Obviously, if this was a real class, the students in here have had that background, but since I'm going to be putting this online, I thought I would start with that disclaimer there. So let's go ahead and get started with this. So today we're going to be talking about the nocturnal low-level wind maximum. Okay, so there are two types of low-level jets that we see in the atmosphere. Number one are what we call synoptically forced and really largely governed by QG theory. So if we have a strong height gradient in the lower levels of the atmosphere, say 850 millibars, we're going to get strong winds there, especially in the absence of deep vertical mixing like you often see in the warm sector of winter season cyclones. And these exhibit relatively little diurnal variability associated with them. And here's an example of a synoptically forced low-level jet. This is just taken from the tornado outbreak we had here in Illinois back on November 17th, 2013. You see an area of 60 plus knot winds from the south in the warm sector ahead of the cyclone here across a lot of the Midwest that produced extreme low-level shear and in the presence of instability. It was one of the biggest tornado outbreaks on record in this part of the world. And then what we're going to be focusing on today is the diurnally forced low-level jet, which reaches a maximum during the overnight hours. And as we see, it forms owing to boundary layer processes. So there's our synoptically forced low-level jet, and here's our other type of low-level jet from Artesia, New Mexico. So these nocturnal low-level jets exist between about 500 and 1,500 meters above ground level. And they're typically characterized by strong southerly winds, typified by warm, moist advection from the Gulf of Mexico or the southern United States, and then that gets transported northward by this low-level jet. And this most commonly occurs during the warm season, which is on its way here over the Great Plains of the United States. And at the end of class today, we're going to talk about some of the geographic variation in there as well. And this can actually result in a nocturnal thunderstorm maximum in parts of the Great Plains. For example, in Omaha, Nebraska, it's most common to see thunderstorms in the summertime, not in the late afternoon or early evening like a lot of you are probably used to, but actually closer to midnight, at which point the boundary layer is obviously stabilized owing to diurnal processes. And a lot of times this takes the form of mesoscale convective systems. So this is from the Markowski and Richardson Mesoscale book. This is looking over a 2-month period in Visay, Oklahoma. No, it's not Vichy, it's Visay, Oklahoma. And you see here it's 6 o'clock p.m. This is local standard time. So 7 o'clock p.m. Central Daylight Time, if you want to spring ahead there. You don't really see this wind maximum in the lower troposphere. And the blue line here at noon, same thing. But if we look at midnight and 6 a.m., that would be the green curve and the brown curve here, we see a distinct wind maximum peaking around 10 meters per second or about 20 miles per hour, around 1 kilometer or a little bit below that above ground level. And I want to remind you that this is taken over in a 2-month period, so that's a rather robust signal to see. If we just look at example soundings here, just from one period in this month, so 0Z, June 16th, 2006. We see typical afternoon sounding on the southern plains. Very capped, no storms this day, but you have your well-mixed boundary layer here down below, capping inversion above that, and actually no cape on the sounding. And winds here down around 850 millibars look like they're about 20 to 25 knots out of the south or south-southeast. If we fast forward 12 hours, though, to 12Z the next morning, notice now what we see, an increase in the moisture down low. Moisture is increased from around 10 to around 14 grams per kilogram in the boundary layer. Diurnal cooling evident here as well. But also notice we have 40-knot winds now showing up around 850 to 900 millibars. And that's the remnant low-level jet often seen on 12Z soundings in this part of the world, which again transported that moisture northward. Looking at surface observations from this example, again in the afternoon, so 0Z, the evening before all of this, temperatures generally around 90 to the low 90s Fahrenheit across Oklahoma. Dew points generally ranging from the upper 50s, occasionally nosing into the low 60s in places. However, if we look now at 16Z the next morning, so this is going to be 11 o'clock a.m. Central Daylight Time, we see the temperatures after cooling at night have warmed back into the low to middle 80s, and dew points have climbed into the mid 60s to in some places near 70 degrees. So that's again depicting that poleward transport of moisture by the low-level jet. Now, in terms of forecasting thunderstorms, one thing that's important to point out is that if we want moisture transport, poleward moisture transport from the source regions of the Gulf of Mexico and the southern United States, we like to see that moisture transport be unimpeded. That is, we don't have large areas of rain or convection, thunderstorms in the way. Because we want that moisture to flow northward, as shown in this example here. However, in this example, we have moisture flowing in off the Gulf of Mexico, but now we have clusters of thunderstorms developing along the Gulf Coast. And inside these thunderstorm clusters, of course, air is rising vertically in the thunderstorm updrafts. So as that air comes northward, it then is transported vertically instead of going northward. And one thing I stress in class all the time is that up and north have two completely different meanings, and those terms should not be used interchangeably. So that air is transported vertically, and as that occurs, the water vapor condenses out, forms precipitation, and then actually rains out of the air. So instead of that moisture being transported poleward, it's transported vertically and then condenses and precipitates out. The onset of the nocturnal low-level jet, also very important in low-level hodograph, low-level wind shear profile modification. Now, if we just go back in time to the tornado outbreak of April 14th, 2012, it was a high-risk day, one of only two day two SPC high-risk days issued in history. This is a sounding from Topeka, Kansas at 18Z, so early afternoon on the day of that tornado outbreak. And we have a little bit of cape here, storm relative felicity 0 to 3 kilometers, only 100 or so meters squared per second squared, so fairly pedestrian here. In the hodograph, again, pretty straight, not really all that curved down low. However, if we fast forward now to 0Z, okay, notice the hodograph has lengthened and become much more curved here down low. I realize the scales of these are a little bit different, but if you focus on the 50-knot range ring contour, you can see, obviously, we've lengthened and enlarged that low-level hodograph. And the reason that occurred is that our wind speeds around 900 to 800 millibars have increased from 35 or so knots up to 50 knots. And that's associated with the onset of the nocturnal low-level jet. And in concert with this, the 0 to 3 kilometer storm relative felicity increased to 451 meters squared per second squared. And I could best sum that up in one word. That would be wedges. So we see the onset of this nocturnal low-level jet increase the vertical wind shear just before and after sunset. And so if we have discrete supercells or sometimes even quasi-linear convective systems moving through such an environment, we know that increased low-level wind shear, increased low-level SRH is more favorable for tornadoes. So we may see a local peak in some cases in tornadic activity near and just after dark. So for example, here's the radar screen grab from the April 14th, 2012 event. And we have several discrete supercells ongoing across the promised land of Kansas, and to nobody's surprise, a large Boeing MCS over Iowa. And if we examine the SPC storm reports, you can even make out in the tornado reports the tracks of the individual supercells moving across northern Oklahoma and a lot of Kansas on this day. And most of these tornado reports occurred actually after 0 UTC, when storm initiation was actually a lot closer, back to 18Z, just several non-tornadic supercells moving across the area in the afternoon. So this figure is actually from Rich Thompson's excellent tornado forecasting workshop that he presented back in the spring of 2015, I believe. And what's shown here on the left are significant tornadic supercell cases. So significant tornadoes defined as EF2 or stronger on the enhanced Fujita scale. And then non-tornadic supercell cases shown over here on the right. The top panels represent the 850 millibar wind speed at 0 UTC. And the bottom panels represent the 850 millibar wind speed in meters per second at 0300 UTC. And you'll notice that in the significant tornadic cases, the winds are slightly stronger than in the non-tornadic cases at 0 UTC, but the max wind speeds here are a little more than 15 meters per second. However, if we look forward 3 hours to 0 UTC, we can see that the low-level jet is quite a bit stronger here. And again, this is a composite of many, many cases, reaching upward of 20 meters per second. So that's 40 miles per hour here. And it is a bit weaker here in the non-tornadic cases. And again, returning to the April 14th, 2012 case, this is an 18Z and a 0Z sounding superposed on top of each other. Again, thanks to Rich Thompson for this figure. And he made all of these available for educational use. But the purple photograph, the purple winds on here, and then kind of the maroon sounding showing up, that's our 18Z sounding. And you'll notice that, again, the low-level photograph, although there's a bit of curvature in there, fairly steady, or fairly not all that long, not something that shouts wedges to me. But then if we look at the green and the red here, that's our 0Z sounding. And the red photograph is a 0Z photograph. And you see that's very long, sickle-shaped and curved, heck of a lot of SRH there. And so what's actually happening as we enter what's called the early evening transition is we see the vertical wind shear increase, okay? And so what that does is, through processes we'll discuss toward the end of the class, if we increase the vertical wind shear, that increases the rotation within supercell thunderstorms, and that results in upward directed forces down low. And so we strengthen the rotation, that strengthens the low-level updraft. And then through the stretching term in the vertical vorticity equation, which is ultimately the final step in tornado genesis, it's an exponential function of time. And you've probably heard a lot about exponential increases in recent days and weeks. But I can assure all of you that if stretching did not increase vertical vorticity exponentially as a function of time, tornadoes simply wouldn't exist on this planet or anywhere else in the universe. So we've cooled the boundary layer here, moistened it a little bit. So you say, well, you cool the boundary layer, you increase it. Yeah, you do a little bit, okay? But that cooling process is somewhat gradual here, okay? And so although we've cooled it, we've also moistened it, okay? So maybe we've increased in a little bit, but we've also increased the cape as a result of that. And we've also increased the low-level wind shear here, resulting in stronger storm rotation, stronger storm scale lift, and better propensity for stretching and tornado genesis. Again, comparing the mixed layer cape here between the significantly tornadic at 0Z and 3Z, these are box and whisker plots. You see again your cape generally remains the same or even increases in some cases due to the low-level moistening as we go from 0 to 3 UTC. The non-tornadic cases, not surprisingly, a little bit less cape showing up there. Also an increase here, but again, more modest cape values in the non-tornadic cases. All right. If we look at sin, however, okay, so our mixed layer sin, we see that the mixed layer sin does increase in the significantly tornadic cases as well in response to boundary layer cooling going from 0 to 3 UTC. And again, remember that surface-based air parcels must first progress through the sin layer before they reach the CAPE layer. Okay, so yes, it is possible to both increase CAPE and increase sin in the same period. But if we look at the non-tornadic cases, number one, we see there's more sin, and we see there's a greater increase in sin, reaching to about 120 on average joules per kilogram, which is a very large value of sin. I kind of consider anything bigger than 50 to be some pretty big sin. So again, if you got a lot of sin, you better get to the virtual confessional there in these times. But I also want to remind you that storm initiation, that storms form generally in low sin environments along boundaries, but then they can progress into environments in which they never initiate with more sin, and I think that's what we're seeing here as well. So to kind of recap what I've been saying in some of the last several slides, the low-level jet forms as the boundary layer begins to cool, increasing the low-level shear. And that can result in stronger low-level rotation and a stronger lift within our supercells. As this goes on, the surface begins to cool, so the CAPE can come down a little bit, or maybe even sometimes go up in response to moistening, but the sin generally increases there. And so this time, kind of just a few hours before to a few hours after sunset, the increase in shear can actually dominate the less favorable thermodynamics, resulting in more tornado production, as long as the surface air is relatively moist. But if you're talking about a high plains environment, for example, where you're maybe 90 over 60, something like that, you'd get a lot more rapid nocturnal cooling following sunset, and thus a greater decrease in CAPE and a greater increase in sin. All right, and then in most cases, eventually the surface cools enough that the storms either dissipate altogether, they could grow upscale into an MCS, of course, or just become elevated above the surface layer, in which case the tornado risk decreases substantially. But in cold season cases, however, these are largely advection dominated. So during cold season, we see a lot less swing in solar radiation between 0 during the day and whatever we see in the afternoon. Whereas during the warm season, we still have no solar radiation during the day, but we have a lot more solar radiation in the afternoon. So we see a bigger range there in the warm season compared to the cold season cases. So these cold season cases, very moist, little diurnal range in temperatures. So sometimes you can actually get the tornado threat going well into the night with these sometimes. And an example of this just from early March 2020, the Tennessee to Cookeville tornadic supercell here. Again, looking at 0Z over here on the left. Temperatures across a lot of middle Tennessee in the upper 50s Fahrenheit. Dew points generally in the mid 50s. But then if we look here, 7 UTC, the Nashville tornado hit around 0630 UTC, so it's 12:30 a.m. Central Standard Time. And notice here that the temperature here actually increased from 58 up to 60 or up to 65. And the dew point increased from 54 to 57 as well. And this is a radar screen grab from this event. And so we have a large MCS going on across a lot of Kentucky at this time. But then a lone isolated supercell on the southern end of this that traversed across a lot of northern Tennessee and actually made it into Cookeville around, I believe, 08 UTC and produced what was an EF4 tornado there. And you can see the track of red dots, storm reports associated with that tornado as it moved across Tennessee there. Our observed sounding from 0Z in Nashville, again, pretty pedestrian photograph, long but straight, nearly moist adiabatic profile here all the way up. CAPE only around 400 joules per kilogram, pretty weak low-level shear as well. Certainly looking at the sounding, nothing to me is going to shout wedges. But now if we allow the low-level jet to work in, and I do want to thank I don't remember who, but somebody at the National Weather Service posted this on Twitter. We see the temperature and dew point here is increased That's increased the Cape now to over 1,000 joules per kilogram. But again, notice these winds here around 850 millibars, increasing to around 50 knots, whereas the hodograph was straight before. Now it's very, very curved down low. Storm relative winds almost normal to the hodograph surface, so almost all streamwise, horizontal vorticity ingestion down there as well. All right, so that covers the low-level jet in tornadoes. So now we're going to move on and talk about the low-level jet and the genesis of mesoscale convective systems. Okay, so this is a vertical cross-section through a front. Could be a cold front, could be a warm front if you want, but we'll just draw it as a cold front here. The light blue lines on this are isentropes, or lines of constant potential temperature. And we know that as air parcels flow here, they, aside from moist processes, they generally remain along lines here of constant potential temperature. So we would expect our air then to flow roughly along these light blue lines. And we'll say the left side of this diagram is north, and the right side of this diagram is south. So if we have southerly winds, say coming up and over an east-west oriented front, maybe somewhere on the plains, as the air parcels impinge on that front and then are lifted over that colder air mass, if the air flowing in the low-level jet is warm, moist, and conditionally unstable, that is, if it has an LFC, it can actually lift to its LFC, and instead of just flowing poleward like stable air would, forming a large area of steady rain or something, it can actually lift to its LFC, at which point vertical convection takes over, and you can get widespread convection, oftentimes forming on the cool side of these boundaries at night during the warm season. So this illustrates this. This is from Bob Roberts' book. We've switched the sides of the diagram now, so again, understand, don't memorize. So south is now on the left, north is on the right, and so here's the warm, moist, conditionally unstable air flowing up and over that frontal surface, being lifted to its LFC and forming elevated convection, that is, thunderstorms that are not ingesting your surface air, but ingesting air from above the surface here on the cold side of that boundary. And we can see this if we look at this histogram of MCS frequency over the central United States. And so time in UTC is shown here on the x-axis, and number of MCSs is shown here on the y-axis. The white bars in front of this are the average starting times, and notice the average initiation times of these MCSs is late afternoon or early evening, around your convective maximum in many parts of the country and indeed the world. And you see this here around 5, 6 o'clock in the afternoon to early evening hours. The hatched bars back behind this is your bar chart of maximum MCS intensity. And notice that that's reaching its peak here around 07 UTC. That's 2 o'clock in the morning. So certainly boundary layers stabilized quite a bit by then, well past my bedtime anyway. And then the black bars back here showing the time of MCS dissipation. And you see they're dissipating kind of around 9 to maybe 15 UTC. So kind of bracketing the time of sunrise the next morning there. So this seems a little bit unusual. So let's look at the low-level jet and look at a case study and help to understand this. So we're going to go back in time here to July 18th, 2007. Stu Ostro of the Weather Channel posted a blog back in 2007 that illustrated a case study for this. So I've taken some of the satellite imagery he used and put that in here, as well as acquiring some of my own imagery from various archives. And we're going to look at an MCS formation over the upper Mississippi Valley, eastern Iowa, western Illinois, and the surrounding areas. So again, sounding from 0Z here in the Quad Cities, Davenport, Iowa. Again, very little CAPE, good amount of SYN on this. Not a whole lot really going on, but again, storms formed not in this location, but north of here. Maybe where things were quite a bit cooler here, a little bit cooler aloft that we see there. If we look at our 850 millibar map, So the solid gray lines represent 850 millibar height in decameters. The red contours on there, the red dashed contours on this are 850 millibar temperatures in degrees Celsius. And the green contours on this represent dew points at 850 millibars in degrees Celsius. So we see some hint of anticyclonic flow flowing around a Bermuda High-like feature here, parked off the east coast of the United States. At the surface, we kind of have this lazy, stationary, or warm frontal boundary from eastern Iowa back into the Dakotas, and eventually extending northwest from there into Montana. So at 9:15 p.m. local time, we see the first hints of convection forming around Dubuque, Iowa here. This is an enhanced infrared satellite image. So this is right around the time of sunset in the warm month of July. And this is an 850 millibar analysis, again, showing the capping here a bit less aloft to the north than down near Davenport and the Quad Cities here. But we see this wind maximum of 30 to 40 knots developing, and that's actually intersecting that frontal surface, which is stalled here just southeast of Dubuque, Iowa. And our surface analysis this evening does show that stalled fronting here. Hazy, lazy, warm sector, temperatures near 80, dew points in the low to mid 70s south of that. And then we see the wind shift here and a little less hot, but still muggy on the north side of that stalled boundary. So if we progress in time, 10:15 p.m., you can see the anvil tops of these storms continue to expand across this area, and then expand even further by 11:15 p.m. And then by 4:15 in the morning, ranging MCS now moving southeastward into northern and central Illinois, with another MCS that formed over South Dakota and Nebraska, moving into Iowa. And so hopefully this works here. We're sharing the screen. Go ahead and do this and load up the radar loop from this. And you can see again, going through in time, you see those first cells developing in northeast Iowa there around 2 or 3 UTC. The time in UTC is at the bottom of the loop here. And then those storms moving or training over the same areas. The front is orient parallel to the mid-level flow. So probably some flash flooding situations developing here as well. And you see that MCS now diving across northern into central Illinois, while another separate MCS develops over northern Iowa. And then by 12Z, 13Z, you see these MCSs here beginning to wane as the low-level jet decays, with, as we'll see, the onset of vertical mixing during the next day. Okay, so now what we're going to do is we're going to talk our way through and go through the mathematical development of the nocturnal low-level wind maximum. Okay, so first, conceptually, so as the moon comes up and the sun goes down, so to speak, okay, the surface begins cooling, and so that's going to reduce the sign of the sensible heat flux just above the ground. So whereas during the day, the surface is warmer than the air above it, so it heats the atmosphere. Well, as the sun almost sets, of course, the surface is receiving less and less solar radiation from the sun, and it's still emitting long-wave radiation. So at some point, it begins emitting more long-wave than it's receiving or absorbing in terms of shortwave. So the surface begins to cool, and then that cools the air above that. And so what that does is it shuts off mixing in the boundary layer. Right, during the day, right, the surface is hot, right, and so that destabilizes the boundary layer and allows for vertical mixing of this warm air through the boundary layer itself. However, as we shut off, as we change the sign of the sensible heat flux down low, what that does is now we're stabilizing the boundary layer. That shuts off the vertical mixing very, very rapidly. And that's important because what that vertical mixing does, other than mixing the surface sensible heat flux through the boundary layer, it also mixes the effect of friction the slowing effect of friction with the surface through the boundary layer as well. And so what actually happens is it's analogous to a spring from physics, whereas if you take a spring and you compress it, okay, and then if you were to let go of that, we'll see in the video in a minute, it's not just going to return to its equilibrium value, but rather it's going to overshoot that a little bit and then oscillate like this about its equilibrium value. And that's what happens to the winds, really, in the upper portion of the old boundary layer, the residual layer, that leftover boundary layer from the previous afternoon. So if I just go here and bring up that video here, just to look at the spring here, because, you know, spring is just around the corner, as we say. And so we see this now is oscillating about its equilibrium value, which is going to be right here in the middle of all of this. And if we didn't have any external influences, like, for example, the sun coming back up the next day, that's what we would see the boundary layer do, again, if we neglect any kind of mixing or anything like that. All right. Okay. And so as we go through the mathematical derivation here, our important forces are going to be the pressure gradient force and the Coriolis force, since, again, friction has been turned off with the cessation of boundary layer mixing. So we're looking, again, not down here in the stable boundary layer near the ground, but up here above that, around 1 kilometer or so above ground level. So what we're going to do is I'm going to stop sharing the screen for right now, and then we're going to transition over to the other camera that shows the whiteboard, and we're going to begin going through this derivation here. And what we're going to do is begin doing this with the U equation of motion, derivation with the V equation of motion. Obviously going to be identical as we've seen, for example, in your dynamics classes, and so to speak. So if we begin with this, let me just grab my slide advancer here so I don't have to keep running back over to the computer. We'll begin with the form of the U momentum equation here, which is just du dt equals -1 over rho dp dx plus fv. Okay, so we'll begin with the momentum equation there, and hopefully that should be relatively familiar to most of you. All right, looks like the slide advancer is kind of wanting to have some issues there. I'm not quite sure why that is. All right. I don't know, maybe it could be out of batteries, I'm not sure. But anyway, what we can do, we'll pull this out and we can advance this. Oh, I know why. It's not, I have to have the PowerPoint thing up on the main monitor. Okay. All right, so there we go. So we now, we can always, now I can't see myself anymore, but we can always break the wind into its geostrophic and ageostrophic components. So our zonal wind U is just the geostrophic plus the ageostrophic component. And we can do that same thing with the meridional component of the wind, which is V there. Okay? So then if I go and substitute this back into these equations, since differentiation and addition are communicative, all right, I'm going to end up now with 2 total time derivatives on the left side of this, the use of g dt plus the use of a dt. And now this is going to equal, again, my pressure gradient force term, which I have not touched, and then plus f v sub g plus f v sub a. Okay? And that's what we have here. Now, one thing we need to do with this is make a simplifying assumption, and that is that the geostrophic wind, our large-scale wind, doesn't change in time. So we're really only looking here around the few hours around sunset, and we can assume for most cases the large-scale weather pattern is not going to change all that much in that few-hour period. Okay, so we're going to assume that that's steady in time. So what does that mean? It means our geostrophic wind here, total derivative of that with respect to time following the flow, okay, is 0, okay? And we also know that equals the sum of our pressure gradient force term plus F times V sub G. That's just our equation for geostrophic balance, okay? So since du sub G dt is 0, okay, we can cross that out of this above equation here. And then since we know the pressure gradient term and the geostrophic Coriolis term also add to 0, those terms there cancel out as well. So that's going to leave us now with the relationship that du sub A dt equals F V sub A, and going through an identical derivation, okay, with the V wind equation, we would see that dV sub A dt equals minus Fu sub A, okay? So what this yields is a system of simultaneous first-order ordinary differential equations. So back in middle school math, high school math, I don't remember when, right? You had, for example, A plus B equals 2, and A minus B equals -2. And so oftentimes what you would do is manipulate one equation, solve for a variable, and then substitute it into the other equation, so you ended up with one equation and one unknown instead of two equations and two unknowns here, u and v, which is what we have, okay? So in order to do this, all right, what we're going to do is differentiate the v equation here. We're going to differentiate this with respect to time, okay? Or I'm sorry, we're going to differentiate the u equation here with respect to time, and then substitute from the second equation, okay? So we can take a time derivative here of the first equation. So this is going to be d squared u sub A dt squared equals F, which is constant in time, times dV sub A dt, okay? So we have this here. And we know from our second equation that dV sub A dt is just minus F u sub A. So this now becomes minus F squared u sub A. Okay. So that is what we have done there. All right. So, so what I'm going to do now is erase this so we can come back up to the top of the board, since I'm kind of out of board space here. So we're going to go ahead and take this off. We'll leave the bottom part up there for right now, okay? But what this yields now is an equation of the form d squared u sub A dt squared plus F squared u sub A equals 0. And this now is just a second order ordinary differential equation with constant coefficients, okay? And so if you've had a course in differential equations, or as we saw earlier in the semester with some of the work we did with the mesoscale instabilities, hopefully this is, let me just check something here. All right, let me just, yeah, okay, good. All right. Things are going along swimmingly there, just checking the recording there. All right. So the solution to an equation like this is just sines and cosines, because, right, if you take, say, a cosine here for u, when you take two derivatives of that, you're going to get a minus cosine, so you can see how these things are going to add to 0. Okay. So our solutions to this set, so u sub A is going to be equal to C1 times the cosine of Ft plus C2 times the sine of Ft, okay? And we can do something very similar for V, and you'll get that V sub A equals minus C1 times the sine of Ft plus C2 times the cosine of Ft, okay? is how this works. All right. So now what we have to do is, of course, just like in a differential equations class, we have to determine our coefficients C1 and C2. So how do we do that? Well, just say, well, at some point, say sunset, t equals 0, okay? And we have some point here, t equals 0, all right? So we know that at t equals 0, right, we have our actual, or we have our geostrophic wind, V, okay? We have our actual, or geostrophic wind V sub G. We have our actual wind V, okay? And we have our initial geostrophic component. This is VA naught, okay? This is going to be VG naught, and this is going to be V naught, okay? So some initial time, we have this initial geostrophic wind component, okay? That's going to be true. So at t equals 0, okay, this is going to be U sub A naught, okay, is going to equal what? C1, now times the cosine of 0. Well, the cosine of 0 is just 1, plus C2 times the sine of 0, okay, which is 0. So this term drops out. So we can see that our C1 is just equal to our initial U component of the geostrophic wind, whatever that is. And we can do the same substitution here with V sub A, okay, where V sub A naught now equals minus C1 times now the sine of 0, so that's 0, okay, plus C2, again, times the cosine of 0, which is just 1, okay? So then it becomes obvious that C1 is U sub A naught and C2 is V sub A naught, okay? And we can make those substitutions up here into these equations for C1 and C2. All right. And then I think what I'm going to do is come back over to the PowerPoint now and start going through those slides. Again, some of the slides, hopefully you can follow along at home there. You know that the PowerPoint is always made available to you online before class. So let me just go ahead and get this back set up here. So we're going to go back, and if you guys would rather see me than the chalkboard, and we'll come back over here, and we need to share the screen. So let's go ahead and do that. Share screen number 2, and share that. All right, and we'll restart the PowerPoint presentation. Okay. Now, we're not going to go through a bunch of trigonometry here. It's important to see some of the derivations, but going through and saying, oh, applying some trigonomic identities, show this. And we're not going to be doing that here in class today. But you end up now with these systems of equations here, where V, the vector V, is the initial geostrophic wind vector. Okay. Then we have cosine of psi naught minus ft and sine of psi naught minus ft. Okay. So what is psi naught? Well, again, we're talking about trigonometry here. So instead of 0 degrees being north, well, 0 degrees is east. And so what that is the offset of the initial geostrophic wind vector. It's basically the angle of offset of the initial geostrophic wind vector there. Okay. And this is drawn such that our geostrophic wind is southerly, meaning we have high pressure to the east, low pressure to the west, and we know that our actual wind, of course, in the boundary layer, in the presence of mixing, crosses the isobars at about a 30-degree angle from high pressure to low pressure. And so now let's interpret these equations. And this means that the wind oscillates about its geostrophic value with a frequency equal to 2 pi over f, which is roughly 12 hours divided by the sine of the latitude. And so if we assume that we begin stabilizing near the surface around 6 o'clock p.m. local time, that would give a max in super geostrophic flow around 3 to 4 a.m. local time at 30 degrees latitude and between midnight and 1 a.m. at 45 north latitude. Just like the spring analogy, the more you compress that spring, right, the more you compress it, the more it's going to overshoot its equilibrium value, whereas if you don't compress it that much, it'll just oscillate here a little bit, okay? And this does not, like I said, oscillate indefinitely like a spring, since the next morning the sun comes up and provides external forcing back to this, and we get low-level mixing developing again. So now that we've kind of gone through this math, let's actually talk about what this actually means, okay? So to do that, we're going to start here, and let me bring the laser pointer back. So here's our initial force balance diagram. And this is our three-way force balance between the pressure gradient force, which acts perpendicular to the isobars toward low pressure. Again, we've assumed low pressure to the west, here with southerly geostrophic flow. We know that our actual wind crosses the isobars at a 30-degree angle toward low pressure or low heights in the boundary layer in the presence of mixing, in the presence of friction. Friction, of course, opposes the actual wind speed, and then the Coriolis force is directed perpendicular into the right of the wind. So this is our three-way force balance between pressure gradient, Coriolis, and frictional forcing. All right. Yeah, that's a big Texan cut. So now if we shut off vertical mixing, what happens is we turn off friction. We're no longer mixing the effect of friction through the depth of the boundary layer. So the friction arrow goes away, okay? So we were in a force balance, and now all of a sudden we're not, because we lost one of our forces, okay? So with turning that force off, basically, what that generates is now our only two forces on this are the pressure gradient and Coriolis. They're not in balance, and so that's going to generate a net acceleration or a net force in the direction of the vector sum of these forces, which is going to be equal to the opposite of the frictional force. It's going to be in the opposite direction of friction, which means it's going to be in the same direction as the wind. So if we go forward now another time step, all right, what happens is, well, we're accelerating the flow in the direction of the flow, so the wind speed increases. In response to that, the Coriolis force, remember, is proportional to the wind speed, also increases, and it's directed perpendicular into the right of the wind. So now these forces are still in balance, but now our acceleration is directed in a different direction here. It's now directed from the south toward the north. So that means now the wind is going to accelerate in this direction. And so you see now that by the third time step, our wind is looking like this. It's now even stronger. And as we go through in time, you notice now that the wind is now overshot its equilibrium point, or overshot its geostrophic value. So we now have this super geostrophic flow in the boundary layer like this, all right? And as we go through in time, again, just taking the vector sum of all of these forces, the resultant is that the actual wind here in red oscillates around the geostrophic value in a predominantly circular pattern, and that's called the inertial circle. And if we look at actual winds, we see that it actually mirrors this relatively well. So going back to that same 2-month period we looked at the beginning of the class today, you see that the wind oscillates around this here. And so it is sub-geostrophic or less than geostrophic due to friction, due to mixing during a lot of the daylight hours. And it's super geostrophic or faster than geostrophic at night, okay? And so this is really what yields this nocturnal low-level jet, and why it only occurs in that residual layer, in that 1 kilometer above ground level layer, because that's where you have mixing during the day and you don't at night, okay? And so going through this, again, this is just an example from the textbook of the night of 15 to 16 June 2006. Again, during the evening, low-level wind speeds here on the average of 25 to 35 knots or so. And then notice here after 9 o'clock, they increase to 50 knots and then 60 knots here in the middle of the night. And then just before sunrise with the inertial oscillation, they decay again and then rapidly decay with the onset of vertical mixing the next morning. Okay. So that is the, and I'd ordinarily pause for questions here as well as several other times during all of this, but again, I'm not doing this in front of anybody. So we'll just continue. And so the last topic we're going to discuss today, and this is also not just one 50-minute class, but it's going to work out to be about a class and a half. And everything actually, the tornado stuff at the beginning of all this, I actually did in person before break. So this map depicts an elevation map of the continental United States. And the wonderful land of the Great Plains, a lot of you think it's flat, but I assure you it isn't. There are little localized hills and things in here. But the broader slope of them, they slope up from around 1,200 feet over the eastern plains to over 4,000 feet, 5,000 feet out here in the high plains. So we have this general slope of terrain upward from east to west, and this also influences the nocturnal low-level wind maximum, and is probably one reason why it's most noticed on the Great Plains of the United States in warm advection regimes. So here, hopefully, again, we remember the thermal wind from our synoptic or dynamic meteorology classes. But the thermal wind, you'll remember, is the vector wind difference across a layer. Okay, so it's not an actual wind, but it's a vector wind difference across a layer. And we know that the thermal wind, if the thermal wind hits us in the back, colder air is going to be on our left. Okay? So here, this wedge-shaped slab here is the sloping terrain of the Great Plains from high terrain in the west to low terrain in the east. Okay? And we see that the thermal wind here is blowing with colder air on its left. Okay, why is that? Well, we know that our warmest temperatures exist right above the ground during the afternoon. And then as we go up above the surface, as we get farther from that warm ground in a convective well-mixed boundary layer, the temperature decreases with height, and it does so approximately dry adiabatically. So this means the higher we are above ground level, the colder the temperatures are going to be on average, all right? So now if we look at the same elevation, whereas that might be ground level over the high plains, temperatures relatively warm, that same elevation is going to be quite a bit aloft, maybe a few thousand feet above the surface over the lower plains. So the temperature at that elevation is going to be cooler, resulting in a thermal wind directed from north to south. So if we look at our actual wind profile, geostrophic wind profile, so that doesn't account for friction near the ground, we're prescribing southerly flow in here. So we have southerly flow at the surface, and then that southerly flow becomes more northerly as we go up, or the magnitude of the southerly flow decreases with height. So that would also yield wind maximum down in the lower troposphere just during the day, but the winds here just decreasing with height monotonically during the day. However, now if we transition into the overnight hours, what happens? Well, at night, what occurs is the ground cools the most. Regions above the ground don't cool all that much. And then as we go above that, well, it's still cold anyway. So let me stop sharing this and actually go back over to the board and draw this up here for everybody. So we'll go back to the board with this. And let me demonstrate this, get some of these equations off of here. So again, if we want to compare day and night, all right, so here's our surface like this. This is just the ground, okay? We know during, oops, got the chair in the way there. So we know that just during the day, yeah, that's still showing up fine. The temperature decreases roughly dry adiabatically with height down in the boundary layer. Okay, so this is going to be our daytime temperature profile. Okay. But now at night, what happens? Well, at night we begin cooling the surface. We develop the stable boundary layer, but we don't convect cold upward, right? Because that's a stabilizing effect. We only convect warmth upward. Okay, so what happens at night is we now get a boundary layer profile looking like this. Okay, So there's our boundary layer profile at night, okay? So what happens is you get this temperature maximum up here at the top of the stable boundary layer, or the bottom of the residual layer, that leftover layer, well mixed layer from the previous afternoon, okay? So we can take this now and apply this to our sloping terrain situation. So let me go back and do that first. Let me reset the camera so it's back on me. All right, so we've done that. And then we'll share the screen here with the PowerPoint. All right, and share, okay. So hopefully we can all see this again now. So our coldest temperatures are at the ground and well aloft here. And we kind of have this warmer, or we'll call it cool, not as cold air, kind of in the middle, like we drew on the diagram, okay? So that means now in the lower part of the very lowest part of the atmosphere, thermal wind again blows with cold air on its left. So that means now it's southerly. So that means southerly flow increases with height just above the ground. Okay, but then as we get higher aloft, well, here's that warm nose here over the high terrain. Meanwhile, over the lower terrain, temperatures again decreasing with altitude. So the thermal wind is still going to be directed from the north. So then our southerly winds decrease with height above that. So that results in a low level wind speed maximum in the near the top of the stable boundary layer into the bottom of the residual layer there. Okay. So again, we see this on the Great Plains because we have this sloping terrain from east to west. I think this is why you see this most prominently on the Great Plains with southerly flows. You have the additional component of the terrain here, okay? And this really sums up kind of everything I just said. And I guess the nice thing about teaching on video is you can always pause this and read this here as well. I lied. We have one more topic to talk about, and that is coupled low-level and upper-level jets. Okay. So this is a 250 millibar map here. The height in decameters are contoured, and then the shading represents wind speed in knots. So if we take a look at this map, we see there's an exit region of an upper-level jet impinging on parts of Texas and Oklahoma in this example. You'll remember from synoptic meteorology that there is divergence aloft in the left exit region of a straight jet streak like this, and convergence aloft and descent in the right exit region. So ascending air here, descending air there. So the air rises, and then we have an ageostrophic wind component flowing across the jet from ascent to descent, like this, at the jet level. So air rises, goes across the jet, and then sinks, okay? And that's three legs of what's called that transverse ageostrophic circulation like this, where there is a lower tropospheric component to that down closer to the surface. But until now, we really haven't paid a whole lot of attention to that. Well, if that lower tropospheric component, which is going to be directed in the exit region from the right to the left side of the jet streak, okay? And in the entrance region, the lower tropospheric component directed from the left to the right side of the jet streak, okay? If that is in the same direction as lower tropospheric flow, well, it can give the lower tropospheric flow an additional component to that due to the transverse ageostrophic circulation there. So here we see is our southerly flow at 850 millibars, low pressure here. I'm right there near Tucumscary in eastern New Mexico. There's our 850 millibar flow flowing like this, and that would be roughly in the same direction as the lower tropospheric component of this ageostrophic circulation we see across the exit region of this jet streak. Okay, and just to refresh everybody's memory, a couple figures from the excellent Gary Lackman synoptic book. We've used that in synoptic and forecasting classes, where here's our upper tropospheric jet here, just southeast of Cold Bay, Alaska, everyone's favorite new town. But here's our left exit region near point C, our right exit region near point D. So looking at a vertical cross section from point C on the left, so that's north on the left, south over here on the right. Contoured on this is omega. Remember, negative omega means ascent. So we have an ascending branch here, and then flow from the left side to the right side of the jet aloft. Descending motion or subsidence over on the right side of the jet, and then flow from south to north down here in the lower troposphere. Now, the in-plane wind isn't shown, only the pressure vertical velocity here. And if you're wondering, well, why is the ascent so much greater than the descent in this case, there may be an orographic component to this, there probably is. Or there may be other large-scale processes ongoing, like geostrophic vorticity advection, differential geostrophic vorticity advection, for example, over in this region. And so that is our transverse ageostrophic circulation. So if we have a southerly low-level jet here, that would be coupled to the upper-level jet through this transverse ageostrophic circulation. All right, so we'll go ahead and stop the share on this. Ordinarily, I'd ask if there are any questions, comments, or concerns about this. But looks like pretty much done going through this, so we'll see how the video turned out, and we'll go ahead and stop the recording.